time for some more Gauss. All right, so we've got two parallel plates. They have, one has positive charge on it, one has a negative charge on it. Since they're close to each other, they've attracted each other, so the charge is all on the inside of the plates, or insides towards each other. And we want to know the electric field in all these 5 different locations with respect to the plates. Okay, the plates are conductors. So we need to do some Gaussian surfaces. What would be a good Gaussian surface? We can do cylinders again. Kind of getting tired of doing cylinders. Cylinders would work here, but let's do a cube just to be different. All right, so let's start with out here. So let's make a cube, 3D cube. So these plates, of course, go back into the paper. They're 3D plates, right, with pluses all over and minuses right on the inside. So we're going to make this cube that goes to the inside of this first plate, inside this first conductor, and then it has these other perpendicular surfaces to the plate, and then it has this other surface that is parallel to the plate, something like that. All right, so each one of these surfaces has an A. That should be straight out. Anyway, 6 different A's because it's a cube, right? And so remember Gauss. Phi, the flux, is E. The flux total is EA. If everything is nice and uniform, we've done it right. EA cosine theta, and then, well, is the sum of our EA cosine thetas, and that's equal to Q enclosed over epsilon naught. All right, so we've got to look at all of our fluxes, add up all these. This is each individual flux for each surface, and see what they are. Hopefully a bunch of them are 0, so we can get a good calculation. So let's draw our field lines so we kind of know what we're talking about here, because remember, we need to kind of know a little bit about field before we can do these problems. But so our field lines are all going straight across, right? They come out of pluses and they go to minuses. Our field lines are all in here. So I don't know, is there much to do here? The field is going horizontally, so all of the surfaces that are also horizontal, that have areas, or vertical actually, this way, facing in or out. So these surfaces with these A vectors are all perpendicular to the field, right? The field's going this way, one A is pointing straight up, one down, one that way, one this way. And so all of those, let's call it, I don't know if we do 1, 2, the bottom is 3, the outside is 4. A1, A2, A3, A4 are all perpendicular to E, implies that phi1 through phi4 are equal to 0. All right, because cosine theta is 90, theta is 90, cosine 90 is 0. Okay, so all of those do nothing. The only ones that could do something are the one pointing in this side, inner side, and the one that's on the outside. Those A's, I guess we will call those 5 and 6. All right, A5 is parallel to E, right? Theta equals 0, theta 5. All right, A6 is parallel to E, but it's in the opposite direction, right? A6 is that way and E is this way, and so A6 is equal to 180 degrees. Okay? Theta 6. So, okay, that's good. So we only have one that we have to calculate, or actually we only have 2 that we have to calculate, and we can just do EA. So let's talk about A5, or surface 5, piece of the surface number 5. So flux 5 is E5, A5 times 1. What is E5? What is E? So this is inside the conductor. We made a little cube with its surface inside the conductor. Inside a conductor, E is always 0. So phi5 is 0. Right? How about out here? A6, phi6, phi6. All right. Well, what is the field out here? There is no field. E is 0 out there also. And so phi6 is equal to 0. So basically we can just by inspection say E1 is 0. Right? Because all the field lines start at positive, goes negative. We have equal and opposite charges, and so they're just going to go straight inside there. So E1 is 0. E2 and E4 are inside the conductors. So they're also going to be 0 because they are inside conductors. Right, we can do a little tiny Gaussian cube inside here. Right, there's no enclosed charge because the free charges, all charges balanced, there's no excess charge. It's all outside on the surface of conductors, and so no enclosed charge, so the E's are 0 on all the surfaces inside the conductors. And hopefully you also see E5 is also 0 because of the field ends, right? The field starts there, ends on the minuses, and so there's no field out here. We could do a Gaussian surface, Gaussian cube out here as well to show that, similarly to what we did for 1, but hopefully you see that it's pretty much the same. All right, so the only one that's really interesting is E3. All right, so for E3, let's see how we can draw this. We're going to make a Gaussian cube, and it's supposed to be inside, so this surface is inside the conductor. Well, it doesn't look like it. It's supposed to be inside the conductor, just like this one was inside the conductor. So the surface of the conductor is coming along here, and it hits and it cuts in. Trust me, it's inside there. Okay. And so we can just do, Let's just do surfaces 1, 2, the backside is 3, bottom is 4 again. Same kind of argument we had through here. A1 through 4 are going in these kinds of directions, and they're all perpendicular to E. E is this way, and these guys are all, E is this way, and these guys are all going up, down, sideways, but with a 90-degree angle to E. So again, for the new case for E3, A1 through A4 are perpendicular to E3, so phi1 through phi4 are equal to 0. Right? Because the angle is 90 degrees, cosine 90 degrees is 0. Theta equals 90 degrees, cosine 90 degrees equals 0, equals 0. All right, so that's good. So now we have 2 more surfaces. We'll call this A6 and this one A5. I don't know why. Now let's do this one 6. That was 6 last time. This one's 6 and this one is 5. Trying to somewhat be the same orientation. And so looking at A6 or phi6 is what? Well, it's going to be E6 A6 cosine theta 6. But what can we say? E6 is the face that's inside the conductor, right? So E6 equals 0 inside a conductor. Okay, so I guess that's not one more strategy for making Gaussian surfaces. If you can make a surface inside a conductor, then you know that the E is 0 in there, so that makes that surface easy to do. Right? If we had used a cylinder, we could have done this with a cylinder, and so all the sides pointing out are all still perpendicular to the field, this cylinder side would be inside the conductor, and so it's 0. The only one that would matter is the one that's out here, which is the same thing we're getting with the cube. So the only one that matters is phi 5. Right? Phi 5 is equal to, well, phi total is just phi 5. Total flux is just the flux through surface 5, which is E5A5 cosine theta 5. And that's going to be equal to Q enclosed over epsilon naught. All right, so E5, I'm sorry, yeah, E of surface 5, but it's really E3 that we're getting too many numbers here. But so all of this is about E3, and we're taking it the E of surface 5 right here. Let's just call it E and take the 5 off because it's going to be confusing. All right, so E on this E right here coming out of the surface, and this is, so that's E, and this is also A5 is pointing out of that surface, and so theta 5 is 0 since E and A line up and point in exactly the same direction. So we just have cosine theta equals 1, and so we can solve this out. So let's go ahead and we're solving for E. What is A5? Oh, shoot. Let's see. So let's just call this length times width. I don't know. It's a cube. So I guess if we call it a cube, then we can just say length times length. All right. So the area of A5 is just length times length. Okay. And that's equal to Q enclosed. What is Q enclosed going to be for this one? Q enclosed is, so where is any charge inside our cube? So remember, this cube goes into the conductor, and then so the face of the conductor that has the pluses on it is inside the cube, right? We need some information about the charge. We'll say that each one of these, since they're equal and opposite, have a surface charge density. So surface charge density, anyway, that's what it is. The surfaces have a charge density, we'll call it sigma. Remember, sigma is charge per square meter kind of thing. If we knew the total charge, we could say sigma is Q over the total area. Or if we want Q, we say Q is the charge density, coulombs per meter, coulombs per square meter times the square meters, right? And so we're just going to use that for Q enclosed. Q enclosed is going to be sigma, the charge density, times the area. 5, which I could have just left there, but we'll just keep working because it's not always the same area. In this case it is. Area is L times L, epsilon naught. All right, so the L times L's go away. So the field is just sigma over epsilon naught, which feels like a pretty weird answer, but it's the right answer. And so the field, does it depend on where we are out here? Does it depend on L, how far out the length of this side of the cube is? No, it doesn't matter on the side of the cube. Doesn't matter if we're right here, halfway in between, 3/4, 2/3, doesn't matter, right? So it's kind of a strange result, but you kind of think of it as a huge plane of charge, and inside where we've assumed that the field is uniform straight across, so we're not talking about the fringy edges, then this is the valid result. So what does the field depend on? It depends on how many charges there are, the density of the charge, how close they are together, and a constant. So really all it depends on is the density of the charge. And so it's a little bit of a strange result, but it's kind of assuming, it's kind of like we're assuming infinite plates. So this distance doesn't matter because these are just huge plates of charge to be able to get the plates have to be much, much larger than the separation to get the field to be uniform, which is what we're assuming. Okay, so in between 2 two charged plates. The field is this, and it doesn't depend. It doesn't matter if we do the charge, we calculate it from here or calculate it from there. They have the same surface densities. They're positive and negative. They match each other up, and so this really doesn't even have to be there. We can calculate the field. If somehow we could get the charges to be, so the minuses make the charges all be on this outer surface, and so that's kind of why that has to be there, but it doesn't really affect the result in terms of anything we need except for to know that the surface density is the same. Okay, let's stop there.